All right, welcome to The Explainer. Today, we're going to pull back the curtain on a hidden language, something that powers pretty much our entire industrial world. You've probably never heard its name, but trust me, it's the invisible force running everything from factories to power grids. So let's just dive right in. So, have you ever stopped to wonder, how does all that stuff actually work? How does a sensor way out on a pipeline tell a computer, hey, the pressure just dropped? Or how does a giant robotic arm know the exact moment to weld a car door shut? How do they all talk to each other? Well, the answer is kind of surprising. It's a digital language that was born way back in 1979, and it's called Modbus. Yep, it's been the bedrock of industrial automation for over 4 decades now. Really, it's the unsung hero of our modern world. So let's get into the big idea here. At its core, Modbus was designed to solve this massive problem. See, back in the day, you had all these machines from different companies, and none of them could talk to each other. Modbus came along and created a universal language. It's a simple, super reliable way for any industrial device to communicate clearly and effectively. So what is it exactly? Well, technically, it's a message structure that controllers can recognize and use. But a much better way to think about it is it's Esperanto for machines. It doesn't matter if they're connected by a simple old cable or some complex network. The core language they're speaking, it's always the same. It's always Modbus. Okay, so how does this conversation actually happen? Well, it's all based on a really clear, really simple hierarchy. It's called the master-slave model. Let's break down these rules of conversation. And honestly, it's a beautifully simple concept. Just imagine this. You've got one device, the master, and it's the only one that starts a conversation. It's the boss, the factory floor manager. All the other devices on the network, they're the slaves, and they only speak when they're spoken to. They just sit there, listen for commands, do what they're told, and then report back. That's it. This whole interaction has a name. It's called the query response cycle. It's super straightforward. The master sends out a query, something like, hey, what's the temperature of sensor number 5? The specific slave device, number 5, hears that, it goes and gets the temperature, and then it sends a response back to the master, like, the temperature is 72 degrees. Every single transaction, big or small, follows this fundamental 3-step dance. All right, so if Modbus is a language, then every single command is basically a sentence. And, just like a sentence in English has grammar and structure, these Modbus messages have a very specific anatomy. And this is where the design gets really, really smart. Each message isn't just a simple sentence. You should think of it more like a formal letter. And this letter is always built from 4 essential parts, making sure it gets to the right place and is understood perfectly every single time. So, part 1, the address field. This is basically the to line on our letter. Every single slave device on the network has its own unique address, a number from 1 to 247. So the master uses this address to direct its query to one and only one specific device. No confusion. Next up is the function code. This is the subject line of our letter. It tells the slave exactly what the master wants it to do. It's just a simple number that stands for an action, like read some data for me, or hey, turn this switch on. Then you've got the data field. This is the body of the letter, right? It provides all the specific details needed to carry out that function. So if the function code was read data, the data field would say which data to read and exactly how much of it. And finally, we have the error check. This is so important. Think of it like a certified mail receipt. It's a mathematical calculation based on all the content in the message. When the slave device gets the message, it does the exact same math. If the numbers match, perfect. It knows the message arrived totally intact, with zero corruption from electrical noise or any other interference. This is absolutely crucial for reliability in a noisy factory. Okay, now this language actually has 2 main dialects, or transmission modes. And these dialects basically determine how the ones and zeros are actually sent down the wire. Let's take a look at the 2 big ones, ASCII and RTU. So on one hand, you have ASCII mode. Here, every byte of data gets sent as 2 characters that you could actually read on a screen. The numbers 0 through 9 and the letters A through F. It's a bit slower, but it's more forgiving if there are little time gaps in the transmission. On the other hand, you have RTU, which stands for Remote Terminal Unit Mode. This sends the raw binary data. It's way more compact, much more efficient, but the catch is the entire message has to be sent in one continuous, uninterrupted burst.
And what's really interesting is how the original guide frames this choice. It says, and I'm quoting here, the main advantage of RTU mode is that its greater character density allows better data throughput. So what does that mean in simple terms? It means you can cram more information into the same amount of time with RTU. And that efficiency is exactly why it's the more common mode you'll find out in the industry today.
Okay, so we've covered the grammar, we've covered the dialects. Now let's get to the fun part, the vocabulary. These are the actual action words, the function codes that make things happen.
Yeah, just think of these function codes as verbs. For example, code 01 is basically the verb to read the status of something, like asking, is this valve open or closed? Code 03 is also to read, but it's for reading a value inside a memory location, like a temperature reading. And then you have something like code 05, which is the verb to force, as in telling a motor to turn on right now.
So we've seen all the individual building blocks, right? The address, the function, the data, the error check. What does an actual Modbus command look like when you put it all together in the wild? Okay, check this out. This is a query taken right from the guide. The master wants to read a sensor value from slave device number 17. So the slave address is 11 in hexadecimal, which is 17 for us humans. The function code is 03, that's our read verb. Then the data field specifies the rest. Start at register number 108, that's 006B in hex, and read a total of 3 registers. See how that works? It's a super precise, incredibly compact, and completely unambiguous command. And that's the crucial point, really. The elegant simplicity of Modbus is its greatest strength. By just combining these few basic parts, address, function, data, you can build these incredibly complex and super reliable control systems. And get this simple, robust system has been around for over 40 years. It was originally developed way back in 1979 for these things called programmable logic controllers, or PLCs, and it has outlasted countless other technologies that have come and gone. Which, it brings us to our final question. In a world of AI, the Internet of Things, and massive cloud computing, why is this workhorse protocol from the 1970s still a cornerstone of global industry? Maybe the answer is that sometimes the most powerful ideas are also the simplest ones. They just work.